Greetings all. This is quantum RNA secondary structure prediction submitted by Team Qudit Creons for the WISER 2026 Moderna challenge. I worked on this individually, and over the course of this project, I built a QUBO formulation for RNA folding using real thermodynamic energies, ran it on real hardware, namely D-Wave and quantum platform. And maybe more importantly, I wanted to walk through two real bugs I found in my own work and how I corrected them, because that process is the big part of what makes this submission solid. Uh, the problem is the RNA secondary structure prediction, figuring out how a strand of RNA folds back on itself into its minimum free energy shape, is combinatorially hard. The number of possible folds grows fast with sequence length. So classical tools like ViennaRNA solve this exactly using dynamic programming, but this doesn't translate naturally to quantum hardware. So the question I set out to answer wasn't just can a quantum computer fold RNA, it was where exactly does a quantum approach succeed? Where does it break down and why? That second part, the why, ended up being most of the actual work. What I built a QUBO formulation using real Turner 2004 thermodynamic energies, not made up reward constants. I solved it on D-Wave using both the hybrid solver and direct QPU annealing and via QAOA on real IBM hardware. I benchmarked everything against ViennaRNA's real MFE output at both small handpicked scale and a proper statistical scale, like 320 random sequences. And every single result was cross-checked against independent ground truth. That last part caught several real bugs, which I'll get into. So coming to the formulations, as the actual math, I represent RNA structure using what I call quartet variables, one binary variable per stacked base pair. So a variable represents is pair ij stacked immediately on pair I plus 1 j minus 1. That's the dominant energetic contribution in real RNA folding. Adjacent stacked pairs are what actually stabilizes a helix. There are two constraints, each base pair at most once. Okay, there's a pairing of at most once, obviously, and no crossing pair, meaning no pseudoknots for now. I do come back to that later. I actually built a pseudoknot permissive extension, but the base model excludes them. The thing I want to highlight here, because it's the actual technical contribution, the energy weight on each quartet isn't a tunable constant I picked to make the optimizer behave nicely. It's the real delta G stacking energy pulled directly out of ViennaRNA's own Turner 2004 parameter tables. Prior quantum annealing papers on RNA folding use heuristic reward constants instead. Mine uses real thermodynamics. On the right, a 9 nucleotide toy example, the total I compute matches ViennaRNA's real answer exactly. So coming to the validation methodology, this is really about how I approach the whole project, not just one component. Every layer, brute force, dynamic programming, the QUBO itself, real hardware got checked against an independent source of truth before I trusted it, not just checked once and moved on, checked every time something changed. That discipline is the reason this whole project is defensible. It's also literally what caught the two bugs I'm about to walk through, including one that had already made it into a hardware result I had published. So there's a major correction in this. This is the most important slide in the whole deck. I want to be direct about it rather than bury it. Months into the project, while I was trying to extend the model to handle bulge loops, a more complex loop type, I hit something that didn't make sense. My bulge aware model, which has strictly more options available than my simpler hairpin only model, was scoring a structure as worse than the simpler model found for the identical sequence. That's not possible if both models are correct. A model with more options can never do worse than a model with fewer. I didn't dismiss that as noise. I traced it down, the root cause, the function that looks up real stacking energies from ViennaRNA's tables was indexing one of the two base pairs in the wrong order. Yes, reversed from what it should have been. The real bug had been sitting in 4 different files since basically the start of the project. I confirmed it systematically, not by inspection, by testing all 36 possible canonical base pair type combination against ViennaRNA's own energy evaluated directly. Only 2 out of 36 matched with the old indexing. All 36 matched once I reversed it. Here's the caveat that actually matters for interpreting everything else in this deck. The structures my model predicted barely changed. Match rate statistics moved by about 1% point either way. But every individual energy value I'd reported anywhere, every DP result, every QUBO result, and every D-Wave and IBM hardware result was off by up to about 1.8 kilocalories per mole per stack. That's rare. I fixed it in all 4 slides, validated everything from scratch, and reran what hardware access I had left against the fix. I could not rerun everything hardware access ran out. That's disclosed honestly, not hidden. So the findings, now into the actual results. First thing I found, and this humbled me a bit, on a handful of small hand-picked test sequences, my simplest model, stacking energy only, no loop penalties, got 4 out of 5 correct. Real against real Vienna RNA output. That looked good. It was misleading. Once I ran a real statistical test, 320 randomly generated sequences, not hand-pegged, the true match rate was 10% and it drops to 0% for sequences 60 nucleotides or longer, which is exactly the length range I later used for hardware scaling test. The energy gap also grows more negative as sequences get longer, meaning the model doesn't just occasionally pick a different fold, it systematically overestimates how stable the structure is because it's ignoring the real entropic cost of unpaired loop regions. So, the obvious next step, add hairpin loop energy, the thermodynamic penalty for the loop at the tip of a hairpin. I built a dynamic program using ViennaRNA's own loop energy evaluators, ran the identical 320 sequence test, and match rate went from 10% to 53.4%. Real substantial improvement. Caveat, because I want to be honest about the process, not just the result. While building this, I found a real bug in my own code. A free multi-loop fallback that was silently zeroing out the hairpin penalty on every single closure, which meant my early version was systematically too optimistic. I caught it by cross-checking my computed energy against ViennaRNA's own structure evaluator, saw they disagreed and traced it down rather than assuming my number was right. Moving to actual quantum hardware, on D-Wave, I ran both the hybrid solver and direct QPU annealing. Direct QPU submission requires embedding my problem's variables onto D-Wave's physical qubit connectivity graph, and that's where I found the real bottleneck. My constrained graph density stays above 47% even at 540 variables, which is way denser than D-Wave's native qubit connectivity, roughly 15 to 20 connections per qubit. What that means in practice, as problem size grows, wall time explodes, 0.28 seconds up to over 40 seconds. But if you actually look at the QPU access time specifically, it stays flat, around 125 to 185 milliseconds the whole time. The bottleneck isn't the quantum hardware, it's the classical embedding search trying to fit a dense problem onto a sparse physical graph. And when it does find an embedding, solution quality on direct QPU was actually 39% worse than the hybrid solver on the same problem, likely from chain breaks in that dense embedding. This is the second real bug I want to walk through, and it's significant. Yes, because it affected results I had already published. I reran my 6 standard test sequences against the hairpin aware model on real D-Wave hardware. 2 of them, the 80 and 100 nucleotide cases, had energies that turned out to be wrong. The original published values were negative 6.90 and negative 7.93. The corrected values are negative 6.20 and negative 6.70. The root cause was branching topology bug. My energy model was allowing a base pair to be treated as closing an empty hairpin loop, when in some selected structures that empty loop actually contained another independent nested stem. I fixed the constraint logic, reran on real hardware, and corrected the record. I didn't delete the old numbers, they are still in the repository, clearly flagged as superseded, so there's a transparent trail of what was wrong and what I changed. So, switching to IBM and QUBO, first problem I hit, the same penalty weight I used for classical exact solving, size to guarantee correctness no matter what, turned out to be about 11 times larger than any single favorable energy in these small problems. That's fine for a classical solver that searches exhaustively. But for QAOA, it meant the landscape was so dominated by that penalty term that the optimizer kept collapsing to the trivial select nothing answer. Confirmed that empirically 0% success across 8 restarts, and I ruled out just needs more optimizer effort as the explanation first. Fixed it with a much tighter QAOA specific penalty that eliminated the total collapse failure mode. But this is the caveat, and that matters. It does not guarantee success. I ran a proper 20-seat statistical suite, and the real success rate is only 15% on one toy case and 25% on another. Even at just 4 to 6 qubits, I want to be direct that an earlier version of this project's documentation overstated this as fixed. Based on a single successful run, I caught that overstatement myself and corrected it once I had the real distribution. First, real hardware run on IBM Kingston 4 qubits exact matched the correct answer, but only 17% of the 2000 shots landed on that correct answer. Compared that to 97% confidence on the noiseless simulator, the gap is real hardware noise quantified directly, not estimated. Second run, 6 qubits on IBM Marrakesh. The best feasible answer the hardware found was a trivial empty structure. The correct non-trivial answer got completely buried by noise. 2 more qubits was enough to erase it entirely. I also caught a bug while looking at this. The single most common answer returned by the hardware was actually infeasible. It violated a constraint with an energy roughly twice what it should have been, consistent with two conflicting parts of the structure both firing at once. I fixed that by ranking all the sampled answers by frequency and picking the highest ranked one that's actually feasible instead of just trusting whatever came back most months. So at one point, I reported IBM hardware access are permanently exhausted. That turned out to be wrong. Access came back, so I reran both toy cases against a corrected model. Both reruns got the wrong answer on real hardware. That's not a real problem. It's exactly consistent with the 15 and 25% success rates I'd already measured. The combined chance of both runs succeeding was under 4%. Failing both was actually the single most likely outcome. What this really did was correct an overstated claim in my own earlier documentation that implied the fix guaranteed success caught by the same validate before test process I have been describing this whole time. Noise study. Two hardware platforms, different signatures. I also ran a real comparison of noise characteristics across both hardware platforms since D-Wave's annealing based noise and IBM's gate based decoherence are fundamentally different physical processes. On IBM, 3 out of 4 runs correct across 3 different backends. Interesting detail, the confidence range for the correct runs, 17 to 24%, actually overlaps with the confidence of the one wrong run, 15.3%. So confidence alone doesn't reliably tell you whether an answer is correct. On D-Wave, all 3 runs found the correct answer and the chain break rate was low. Under 7 out of 1000 reads had any break at all, but the read level confidence, how often the correct answer specifically came up, was 8 to 10 times lower than IBM's. Chain breaks alone doesn't explain that gap. With only 3 D-Wave runs, I can't fully diagnose the mechanism, but the finding itself that per read confidence stays low even with minimal chain breaks is real and worth reporting. So now one of the optional advanced tasks, with comparing my quartet based encoding against an alternative raw base pair variables, the encoding style used in earlier literature. Both represent the exact same physical model, just structured differently. Real consistent finding across every sequence length I tested. The raw pair encoding needs about 3 times more qubits than my quartet encoding ratio between 2.94 and 3.67, but has a somewhat less dense constraint graph. real trade-off between qubit efficiency and constraint density, not a free win either way. There's one more thing I caught and verified rather than dismissed. At one sequence length, both encodings found different structures that were tied at the exact same optimal energy. Confirmed independently that both were genuinely valid, equally optimal answers. A real degenerate optimum is the underlying energy landscape, not a bug in either encoding. Pseudonauts. Crossing base pairs are excluded by the base model. General pseudonaut folding is NP hard, so I didn't attempt that. What I did do, relax the no crossing constraint and prove the solver correctly exploits it when a crossing structure is genuinely favorable. I hand built a test sequence with two independent stems specifically designed so that they have to access they had have to cross to both to be used, verified programmatically, not by eye, that they really do cross without allowing crossing. Best answer uses only one stem, negative 8.70. With crossing allowed, the solver correctly finds both stems together. Negative 17.40, which exactly matches what I calculate by hand should happen if both stems energies just add together, since they don't share any bases. I did not add real pseudonauts specific loop topology energy penalties. The extra thermodynamic cost that a real crossing structure incurs is beyond simple tracking. My crossing quartets are scored identically to nested ones. That's a real simplification stated directly, not hidden in a footnote. So here's the honest state of what's not done. No multi-loop support anywhere. Neither the dynamic program nor the QUBO handles multi-branch loop structures. The QUBO still lacks bulge and internal loop energy. I proved with a dynamic program that adding it would help. That's the single biggest remaining gap in the actual QUBO. No real pseudonode energy penalties, as I just said. QAOA succeeds only 15 to 25% of the time, measured directly, and I confirm via classical simulated annealing that this is a genuine landscape difficulty problem, not a bug in my formulation. IBM hardware noise dominates by around 6 qubits on current hardware without deeper error mitigation, and D-Wave's qubit access trigger pattern, which sequences actually engage the QPU I did resolve. It turned out to be caused by constraint density from branching topology fix, not an unexplained size threshold, confirmed with repeated real hardware runs. So the future work, there would be real prioritized next steps, not a vague wish list. Highest priority would be given to port bulge and internal loop energy into the actual QUBO. The dynamic program already proves it's worth doing. So proper multi-loop support next, implementation. On the QA/OS side, either problem-specific circuit depth tuning or a different reformulation entirely. Since a blanket depth increase doesn't generalize, I tested that directly and it helped one test case while making another one worse. Real pseudonode energy penalties, extending the D-Wave noise study across more qubit counts and rerunning historical hardware results against the indexing fix wherever hardware access becomes available. Again, that's genuinely the top priority if I get more hardware die. So everything in this presentation came from checking results against independent ground truth and being willing to say that doesn't look right even about my own already published numbers. I found and corrected 2 real bugs during this project, one of which had already made it into hardware results I had shared. I think that process, not just the final numbers, is what this submission actually demonstrates. Thank you. You can check the repository. Thank you, Slovan.